Hello, math learners! Our lesson for today is about the basic concepts on circles. These are the learning objectives. You are going to define and identify the parts of a circle. State theorems related to the parts of a circle. And illustrate the parts of a circle. These are the primary parts of a circle, namely the center, the radius, diameter, chord, tangent, secant, and we have also the point of tangency. Now, what is a circle? A circle is the set of all points that are of the same distance from a given point in a plane. The given point is the center of the circle. Circles are named using capital letter, like circle O. For example, let us have circle O. And this is the illustration of circle O, where the center is point O. Next, let us have the radius. The segment from the center to any point on the circle is called the radius. And the illustration is this one. This is radius OP, and this is the symbol of the radius. So from O to P, this segment represents the radius of the circle. Let us have a chord. A segment whose endpoints both lie on the circle is called a chord. For example, in circle O, we have a segment AC, and this is called chord AC. Let us have a diameter. A chord that passes through the center of the circle is called the diameter. For example, in circle O, you have a segment passing through center point O, and this segment is considered as a diameter. This is diameter AC. We also have interior of the circle. The set of the points in the plane of a circle whose distances from the center are less than the length of the radius is in the interior of the circle. For example, here, the interior points or the points in the interior of the circle are A, C, D, E, and F. Look at this. The distance from the center to point C is less than the distance of the radius. That is why they are considered as interior points of the circle. Next, exterior of the circle. The set of points in the plane of a circle whose distances from the center are greater than the length of the radius is in the exterior of the circle. For example, we have exterior points A, C, D, E, F, and G. And the distance from O to E is greater than the length of the radius. That is why they are considered as exterior points or the points in the exterior of the circle. Let us have secant. Secant line is a line that passes through the circle. Thus, it contains a chord. For example, this is a chord DE. And if it is extended, it becomes a line. So, this is now called secant DE. And the symbol is the symbol for line. Next, tangent line. Tangent line or tangent is a line that intersects a circle at exactly one point, which is called the point of tangency. For example, supposing this line with point A and E, and point A touches the circle. This point A is what we call the point of tangency. And this line is what we call tangent AE. And again, A is the point of tangency. Let us have example on the primary parts of a circle. So we have center point O, then let us draw a circle. And we have point A connect with point O, that's the radius. We have point C, and then point E connect, then we have the diameter. Point D, then connect with C, we have a chord. And we have point J as the interior point. We have F, B, point I, connect point I and F. Then we have secant line. And then we have point H, G, we have tangent line, and the point of tangency is point D. So again, let us name them. The circle is named by its center point O. So the red circle is named as circle O. Then segment OA, OC, and OE are examples of radii of the circle. Radii is the plural form of radius. Then we have segment CE, which is the diameter. It passes through the center point O, or two radii OE and OC. We have CD, which is a chord. We have points O and J are in the interior of the circle, or they are called interior points. And we have points F, H, B, I, and G as exterior points, or points in the exterior of the circle. We have line AE that passes through the circle, so meaning it contains a chord, so it is called secant or secant line. Or we can name this as secant line FA or FE or AB. Just choose two letters on the line to name the secant line. We have line HG, or you can name it as BD or DG or HB. And that is the tangent line that intersects the circle at point D, in which point D is what we call the point of tangency. Take note, letters may interchange if it is a segment or a line. Next, let us have the segment of a circle. Now that we have these parts of a circle, this allows us to relate them to each other. We can form these theorems that will show the relationship between some parts of a circle. The following theorem provides the relation between chords and radii and their proofs. Let us have the radius chord theorem. If a radius of a circle is perpendicular to a chord, Then, the radius bisects the chord. Let us have this illustration. OP is the radius, MN is a chord, and this radius is perpendicular to chord MN, meaning it forms a right angle. Let us have the proof. Given OP, which is perpendicular to MN at point Q, we have to prove that segment MQ is equal to segment QM. And this is the proof. First statement, OP is perpendicular to MN at point Q. That is the given statement. And angle OQM and angle OQN are right angles. That is from definition of perpendicular segments. If the two segments are perpendicular to each other, then they form right angles. Triangle OQM and triangle OQN are right triangles. The reason is the definition of a right triangle. A right triangle has a measure of 90 degrees or considered as a right angle. The fourth statement is segment OM is congruent to ON. That's the definition of a radius of a circle. OM, that's the radius. ON, that's the radius. The radius is equidistant from the center to any point of the circle. Next, OQ is congruent to OQ. This segment OQ can be equal to itself, and that is under reflexive property. Next, we have triangle OQM is congruent to triangle OQN. The reason is hypotenuse leg triangle congruency. Hypotenuse leg triangle congruency states that if the hypotenuse and a leg of one right angle are congruent to the hypotenuse and a leg of another right triangle, then the two triangles are congruent. And therefore, segment MQ is congruent to segment QN. And the reason is congruent parts of congruent triangles are congruent. Let us have the converse of radius chord theorem. The given proof of chord theorem simply tells us that a radius bisects a chord when the two are perpendicular to each other. Now, let us consider the converse of the theorem. It states that if a radius of a circle bisects a chord that is not a diameter, then the radius is perpendicular to the chord. Let us have the illustration. If this radius OP bisects chord MN, which is not a diameter, then the radius OP is perpendicular to chord MN, and it forms right angles. Let us have an example. In the figure on the right, CE is perpendicular to AD at point B. If the length of the radius is 7 and CB is 3, what is the length of AD? So by the definition of radii of circles, we can say that CE is equal to AC, which is also equal to CD, and the measurement of each radius is 7. Using the Pythagorean theorem, for triangle CBA, we can find the length of AB. That is, the Pythagorean theorem states that the square of the hypotenuse is equal to the square of the base plus the square of the altitude. So, to solve for AB, then we have the square of AB is equal to the square of AC, which is the hypotenuse, minus the square of CB. And then let us substitute. The value of AC is 7, which is also the value of CD, minus 3, which is the value of CB. Take the square of 7 is 49, the square of 3 is 9. Then subtract, it's 40. Then extract the square root of both sides. Then we will have AB is equal to the square root of 40. And then you can simplify the radicand by factoring the radicand. So we have 4 times 10. So the simplified answer or value of segment AB is 2 times the square root of 10. Therefore, to find the length of AD, we have to get twice the value of AB. From A to B, that is 2 square root of 10. So AD is equal to 2 times 2 square root of 10, which is equivalent to 4 square root of 10 units. And that's the measure of segment AD or chord AD. Next example, in the figure, CE bisects chord AD at point B. AD is equal to 16, so AB is equal to 8. BC is equal to 6. What is the length of the radius of the circle? Given that AD is equal to 16, then AB is equal to BD, which is equal to 8. Since CE bisects the chord AD at point B, likewise, the converse of radius chord theorem states that when a radius of a circle bisects a chord, then they are perpendicular to each other. Then we can say that triangle CBA and triangle CBD form congruent right triangles. Using the Pythagorean theorem, we can solve for the length of the radius. So, let us use triangle CBA, and the hypotenuse is AC. So, let's take the square of AC, which is equal to the square of AB, that is the base of the triangle, plus the square of the altitude, which is BC. And solving for AC, we have to substitute 8 to AB and 6 to BC. Then take the square of 8 plus the square of 6. The result is 100. Then we have to take the square root of both sides to solve for AC. So AC now is equal to the square root of 100, and AC is equal to 10. The length of the radius is 10 units. Let us have another example. In the figure, OL is perpendicular to GK at point H, where GH is 5x minus 9 and HK is 3x plus 11. What is the length of GK? Since OL is perpendicular to GK, then GH is equal to HK. Thus, using GH equal to HK, 5x minus 9 is equal to 3x plus 11. Then we have to transpose 3x, it becomes negative 3x, transpose negative 9, so we have positive 9. Then 5x minus 3x is 2x, 11 plus 9 is 20. And divide both sides by 2. So we have x is equal to 10. Then using the value of x, which is 10, to find the length of GK. So, for GH, we have 5x minus 9, change x into 10. So, we have 5 times 10, 50 minus 9 is 41. And for HK, we have 3x plus 11. So, 3 times 10 plus 11 is equal to 41. So, JK now is equal to GH plus HK. That is 41 plus 41 is equal to 82 units. Let us have the chords of congruent circles theorem. In congruent circles, if two chords are the same distance from the center, then they are congruent. Let us have the first circle X and the second circle B. This theorem simply tells us that if circle X is congruent to circle B and segment XZ is equal to segment BD, then chord WY is congruent to chord AC. Do you have questions? If there is none, then see you next time. Bye!